All right, welcome to class. We're going to talk about the characteristics of network media used in Ethernet. What are the characteristics of Ethernet in early age? We had the bus network, right? Everything was connected to one medium going back on the backside. Then we got brilliant and said, hey, why don't we connect everything to a hub to one device instead of one medium? Everything connects to that one. And that's where you come in to a physical evaluation of a star topology, but still it was it was a bus because they all connected still peer-to-peer. Then we came out with the emergence of a LAN switch. What is a LAN switch? Well, that's the device that allows you to connect multiple computers to your network. And when you did that, it broke it off to where every computer can talk at the same time now, and packets get switched at the time they need to. Instead of having a collision domain, you now have two different collision domains. So, what's the difference between a WAN man and a LAN? Armand? What is the difference between a LAN, a man, and a WAN?
LAN is like right here, and WAN would be the whole department, wireless.
No, it's not wireless.
I mean,
David, what's WAN?
It's a wide area network, so it could be like the entire university. And then the metropolitan is like if it was confined to like a city,
Exactly.
or a regional area.
Most people want to think of WAN as the internet.
Yeah, but
But we defined 802 standard is your communications medium standard, which means if it's wireless, it'll be 802.11s. If it's Ethernet, it's going to be the 802.3s or 802.2s. 802.2 is your logical link layer of the data link layer on the OSI model, and that's what gives that standard to it. And then you have the 802.3, which is what all we know is the physical medium, the RJ45s, your true Ethernet capability. Can I show you got it? Okay. You just give me that look like, I'm not sure what he's talking about. The difference between layer 2 and layer 1. Layer 1 cannot communicate with any of the upper layers. The upper layers have to grab the data and take it up. So layer 2 connects to the logical link layer and passes data up. Layer 1 cannot see devices. Layer 2 can. Layer 1 only recognizes bits as they come across. Layer 2 can take those and compact them into frames and get the data out of it. So, as you can see, layer 1 basically all it does is read ones and zeros all day long. That's all it does. Now let's talk about the media access control layer of the data link layer. What is it responsible for? Well, it's responsible for the media in data encapsulation of the frames, addressing and error correction, like we talked a little bit last lecture. A data link, the MAC layer takes the frame, compresses it, sends it down to layer 1. That's all it does. It takes the data and puts it on the media and takes it off the medium. That's it. Pretty simple, right? Y'all confused? Okay. The physical devices are on the physical layer. Okay, layer 1. Those are going to be your UTP patch cables, your Ethernet fiber connectors, Ethernet switches. Those are all your physical medium. Okay? What media access control does is it makes sure that the CMSA CD, and if the frames are not received on the other end, it'll retransmit the frames if it detects that there's a collision. Okay? That's what collision detection means. Carrier sense multiple access collision detection. I mean, someone rang the doorbell, I heard it. I detected that someone rang the doorbell. Someone rings the doorbell, has a gun, what am I going to do? I'm going to avoid them. That's collision avoidance. You get up, go out the other door, right? That's the difference. CSMA CD, all it does is it listens on to make sure that every packet gets to that device that needs to. That's all it does. And it listens to make sure that no one else is on the line before it sends anything, so that there is not going to be any collisions. All right. I'm not going to worry about the difference in the frame and encapsulation. The MAC address is your Ethernet address. Y'all know what a MAC address is, right? It's the physical or the physical address of that system or that network interface card. All it does is says, okay, this frame is going to go for D. Well, A saw it and said, no, not for me. E, B, C, and G all saw it. F saw it and said, nope, not for me. D says it's for me, so they got it. That's basically how it works. The hexadecimal numbers, decimal to binary equivalents. So if you had a 0 to 15, you see how it does it with the octet of 4. If you need to go bigger than that to make a byte, you're going to have your FF, up to 255, which would be your entire octet is set on ones. Does that make sense?
Can you repeat that?
Okay. The decimal and binary to hexadecimal for a single half octet, 4 digits. There's only 15 possible combinations. Remember 0 or 16, 0 to 15. Remember if you take that and if this is 1, this is 0, this is 0, this is 0, what do you have? You have 8. Right? If I turn on the first 2, I've got 8 plus 4, which gives me 12. You see how it goes? Basically, you're looking at a full octet when you were to turn them on or off. The binary value will tell you what the decimal value of it is and the hexadecimal value. That's all it is. All right, here is what we call a Ethernet packet or Ethernet frame. You're going to have a destination MAC address, source MAC address, destination IP, source IP, and the user data. Now, the destination and source IPs in the user data are all in the IP packet. A frame just adds the MAC address information and a trailer. This is here's the end of the pack or the end of the frame. That's all it does. Y'all understand that? Okay. When you used to use a hub, you would always, if you connect a hub to a hub to a hub and you're adding all these computers together, you're still in one collision domain. It has to go to every single computer to find out where it needs to go. All right? All the computers share that one bandwidth slot. So you can imagine if everyone flooded the traffic, what are you going to have? The more hubs you have, the bigger your collision domain is going to be. All right? When you put a switch in there, it breaks off your collision domain, but you're still all in the same broadcast domain. All right? A switch uses basically it acts between all the computers as a shared medium resource. So you have all the computers are going to collect into it. Now, if you put a hub on either side, what you're doing here is saying, I've got everything on this side is 1, everything on this side is 1. A collision domain, collision domain. As you can tell, a switch breaks up collision domains. If they all directly connect into the switch, then each computer itself becomes its own collision domain, and it's not talking to anything else but that switch. Does that make sense now? Look at the top graphic. By having a hub, all the computers have to talk together on the same bandwidth line. So that'd be like all of us talking. We're in this room. We're all talking at the same time. Okay? How much work is going to get done? None. A switch would come in here and compartmentalize each one of us. And so if we're all talking at the same time, it's all going to that wall, which would have been the switch. And so now we have 5 different collision domains. But once you add a hub in there, and those computers connect to that hub, you've increased your size of your collision domain. All right? I'm not going to worry about switching logic. You don't need to know it. ARP, Address Resolution Protocol, is just like DNS. Okay? With the exception, DNS takes a colloquial name, like Contoso.com, and translates it to an IP, right? Because we don't remember all the IP numbers for every single server in the world. If I want to get to Microsoft, I'm going to say Microsoft.com, right?
Yep.
I don't know that it's 123.68.42.10. Okay? I don't know that. And I'm sure that's not it anyway. I'd be surprised if it was. So you're taking it in that same type of thought process. It takes your IP address and maps it to a MAC address. So the computer knows an IP address, but it's going to map it to that MAC address, which is your physical machine. Remember, IP addresses are logical addresses. They are not physical addresses like a MAC is. So all it does is it compares. So if I'm reading a table and say, okay, I need to go to 10.1.1.1, that's Armand's computer. 10.112 is going to be David's computer. So if I'm sending a packet and saying I need to go to 10.1.1.2, it goes, okay, well, you're going to go over this MAC address of F0AB6 Delta Charlie Edward Foxtrot Alpha. Okay, that may be his MAC address. And that's all it does. It says, if I need to go to this MAC address, here's where you go. Same idea of what DNS does. Is all it does is look to the other one. Now, with reverse address resolution protocol, or RARP, you take the MAC address and you're translating it back to an IP address. That's the only thing it does. Does that make sense? Did I explain that pretty well to you, hopefully? So if I quiz you on it. Okay. ARP destinations, when it's looking for destinations outside of the network, it takes that data from that MAC address and says, oh, I looked at the IP address. I can know that it's on this network. So it goes out this port, and I don't care where it goes after that. Excuse me. All right? Like I said, all it does is take that 10.10.0.3, and there's the MAC address. And it goes, if computer C was removed from the network and I'm trying to get that packet out there, it's still not removed from the ARP cache. So A can still try to send it to C even though the C is no longer on that network. Okay? ARP broadcast, all it does is says, here's where I am, here's my IP address, and here's my MAC address, so it updates their own routing table on that computer. It's address resolution table. Does that make sense? I'm getting blank stares. Okay. An address resolution protocol, broadcast address. Okay. What it does is it sends it to everyone, and all it does is says, hi, I'm Scott. My IP is 2.10.10.10. My MAC address is 64. Blah, 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 blah. You then take that information and put it into your computer. Well, your computer will take it and put it into a table. The MAC address to that IP address. So if I need to send you something and it's going to go to an IP address, I can add the MAC address on the front end of that frame and send it on. If you're inside my internal network. If not, it goes out the switch, and the switch sends it out to the router, which will then forward on through the routing table, depending on what port it's connected to what network it needs to go to. Does that make sense? Okay. Now let's talk about Chapter 10. Network fundamentals. Woohoo! What devices do you need to make a LAN? What do you think?
And a switch,
You need a switch.
cables, right, on what the network is, but you need the right cables. Like you can use Cat5 or Cat twisted pair.
Okay, Ben Chill, what do you think? What else do you need?
Need the router,
Well, you need a router. Lance, what do you think? A computer? That'd be kind of important, right? You want to plan logically and physically how you're going to lay out a network. You don't want to just leave stuff hanging out. Okay? And some of the aspects that you need to think about is, how much is it going to cost me to do this? Networks are not cheap. How many ports do I have? Do I have the scalability to increase my number of ports? And do I want to be on a 100 megabit network, a 10 megabit network, or a 1,000 megabit network / gig network? Am I expandable? In other words, can I put another couple modules in there and make my system function better? Okay. Is it manageable? It means I have the expertise there to manage that network and keep it running. These are things you got to think about when you're implementing these networks. All right. The basic LAN network is 2 computers and a switch. That's it. Assuming you plug the computers in to the switch. That is the basic network. Now, you can have a lot of different varieties. You can have multiple switches in your network that connect to other switches. You can have 2 central switches with redundancy to every other area. You can have one large where everything connects into one switch. I mean, you can make it as much as you need or as big as you need to focus correctly. All right. What type of connections are in a LAN? Well, let's start talking. First off, the back of your computer, you have a NIC in it, right? It's connected into the wall jack that's on the wall, which is fed up into a patch panel. Then you have a what do you call them? You will have a patch cable that goes from your patch panel to your switch. Your switch will then run out from your backbone to the router that will feed it out. That's essentially all it is. So from our computer, we're going to the wall jacks. Y'all can physically see the wall jacks, but from there, that's where you can't physically see it anymore. But it will connect into a patch panel down the hall, into the switch, which is fed with the packets out to the school's network. All right. And here's just an example of how you can have many different types of connections. If you're going, and here's the easiest way to remember cabling. If you're going from one level of the OSI model to another, it's a straight through cable. Okay? If you're connecting to a device on the same level, i.e. a layer 2 switch and layer 2 switch, you have to have a crossover. Layer 3 router, layer 3 router, you have to have a crossover cable. Because you're switching the receive and transmit pair. That's why it has to be a crossover. Speaking of the pairs, straight through cable, you're going to have you're going to use 56AB. And what that's going to be is it's going to be white, orange, orange, white, green, blue, green, white, brown, brown. 568A, you can use on both ends. But usually when you see a 568 end, which means you're going to have the white, green, and green on the end, it's going to identify that cable as a crossover cable. You're not going to see a TIA 568A cable in an infrastructure anywhere unless it's a crossover cable here in the United States, because everyone goes by the B standard. All right? So it's just an easy way to remember. If you see green on the left side, you know it's automatically a crossover cable. If you see an orange side, take a look at the other end. And if it's orange, great, you got a straight through. That's it. The only difference is the orange pair and the green pair are swapped. That's it. The blues will always be 4 and 5, and the browns will always be 7 and 8. You're going to have two different types of WAN connections. You're going to have a smart serial or Winchester block. You can use serials, you can use 449s, you can use V25s, you can use a high-speed serial interface. There's a lot of ways you can connect an interface for your frame relay or PPPs from router to router. Okay. In DSL modems, you're going to have an RJ11, obviously, because that's a phone line. And then you'll have your cable modem, which is an F. Basically, it's going to be an F-type connector. And you can use those as RJ45s too. But it's mainly fiber. Well, if I'm going to make a change into console into a Cisco device, or any device for that matter, if I need a console in, one is going to be on a serial end. Why? Because that's your COM port. That is your telnet port on your computer. So you can use your RJ45 to DB9 connector, which is what we call a rollover cable. And it's very flat. It's blue, kind of a light sky blue. And it'll connect the terminal adapter into the device. It has RJ45 on one and it has a serial connector on the end, on the other end. Serial connector goes in the computer, RJ45 goes in the device. You can telnet in. Pretty simple. You want to make sure that you have it at 9600 bits per second, so that you can communicate directly with the port. You've probably seen these quite a bit. You're going to have administration computers, switch management, IP phones, printers, routers, servers. You've seen these throughout your packet tracers, right? But when you're designing them, you want to use these type of logos to better associate, so everyone in the field knows exactly what you're trying to say and how you're going to design something. All right. I'm not going to worry about you calculating those range. Why is it important to know the total number of hosts in a network when you're subnetting out? Because you want to make sure you have scaled a big enough network for those hosts. All right? One thing I like to do when I'm doing networks is, if it's going to be a backbone line, I like to make it red. The keystones, jacks, the wall jacks, the lines, they're all red. So when I see a red, I automatically know this is a backbone line. Blues are going to be my patch cables. They'll go from the computer into the walls, and those will be going directly back to switches. Okay. I like to use yellow for printers. So when I see the yellow jack on the wall, I know that's a printer port. In gray, I use that for practically everything else. And when I have a router going into a switch, that's always going to be a red. So when you see it, when you're looking at the switch and you see a red line going in, you automatically say, okay, this port right here is going to be going to my backbone. Here's a yellow one. Oh, well, that's going to the printer off of port 24 off this switch. It's easy to identify that way. Yes?
When you say colors, do you mean?
The color of the Cat5 cable.
Oh.
You can have jackets on them. You can have wall keystone plates that are those colors. And it makes it easier to identify what's what. Because if I put everything as white, I'm not going to know. Right? You want to make sure you count your subnets. Why? How many subnets are there? Could it be 6? Remember, the computer is only signaling that there's a LAN connectivity to it. But in this instance, there's only 3.
But it could be more than 3, right, though?
Oh, yes.
On the network.
It could be a lot more than 3. What is the role of the iOS? Internet Network Operating System. What do you think it is? It's that command line interface that you see. It's the operating system that runs on these devices. That's all the iOS is. It's an embedded device, and it starts out with what we call startup configuration. That startup configuration file is what is in ROM, or NVRAM. Non-volatile random access memory. Okay? That's where it stores it. Then, when the machine is clicked on, it takes that startup config and loads it into what we call the running config. So that's what can be changed all the time. Until you copy your new running config back over to start, your running config is what's running your router or your switch. Does it make sense? And you'll see how this plays out as we go a little bit longer. The hierarchical mode. Okay? You have a user executive mode. All that means it's very limited. You can't do much with it. So always jump to the privileged mode. Now, how many of y'all taking Unix Linux? David? Armand? Okay. A $sign at a command prompt. What does that mean to you?
Oh, that's like the admin mode.
No, that's the user mode. That is user exec mode. That's all it is. You see a pound sign. What do you think? Root, privileged, things of that nature. The iOS is based off of a Linux/Unix platform. The commands are going to be very similar. Okay? Then we have what we call a global configuration mode, where you have the user or the device name, and then in parentheses, configure or config, close it out. But it's inside of the privileged mode because that's where you do all your configurations at. Then we have our interface mode, which is a configuration of the interface. So your interface is to configure an interface is a sublevel of the configuration profile, which is a sub of the overall privileged mode. Does that make sense now? So if you want to get down to configuring an IP on any device, you have to go through 4 steps. You got to log in, then you got to change into the executive, change into configuration, and change the configuration of that interface. That's it. Okay? And we're going to start getting into these a little bit more next week when we start dealing with the command line. Okay? So I want you to go through this weekend and I want you to look at all these different commands that are in this slide or in this slideshow for 11 so that you can get it through and kind of basic understand it. All right? When we get next week, you're going to go over and we're going to go over and I may give you a quiz, a pop quiz on this slide right here. What's an NVRAM? What's flash? How do you get to them? Okay? So don't be surprised. iOS configuration modes. Like I said, your exec mode, instead of a $sign, you have the greater than symbol. Privileged mode, you have your asterisk or your pound sign. Global configuration mode, and then your specific, whether you're configuring the router, a console line or TTY line, or a configuration of an interface Those are the commands that you'll deal with. Here's the back of what you're going to have on an iOS device, such as a router. This is a router. It gives you a fast Ethernet port, a Telnet port, and they will tell you specifically on there. Blue is going to be your console port. Black will be your auxiliary ports. A dark blue is going to be your serial ports. Yellow is going to be your Ethernet ports. So if you're looking on the back of a Cisco router, you will see these colors. Even if you can't read it, if you can see the color, you know what to put into it. All right. Why do you want to name devices?
To identify them.
Right. Because if I said students, and all your names were student, and I say student, who's going to look at me? All of you. Right? If I said Armand, the rest of you are going to ignore what I have to say because I'm talking to Armand, right? That's why you give a name to it. It also helps identify it, maybe a location. For example, Atlanta headquarters, Atlanta HQ, and I put -R. Why do I put a -R? Because that identifies it as a router. I can have Atlanta HQ as a switch too. So if I do that -R out after Atlanta HQ, then I know that that's the router for Atlanta HQ, and S, and I can be S1, S2, S3, whatever. You want to make it very specific as to where that location is when you're identifying or naming a switch or a router. Okay? There's different things that you can do. I'm not going to get into the command line until we start talking next week. Okay, I don't want to overload you with too much. Log on banners, you'll need to know that. And we're going to talk about how to get through and see different things. We're not going to do any TFTPs in here. We're not going to do any hyperterminals, but you're going to be able to do this through Packet Tracer. We're going to talk about shutting down and no shutdown, the differences between those. We're going to talk about the interfaces and how you configure them. When you give a description, you know what that description for that particular interface is going to be. Host parameters, how the data travels back and forth. Okay, how to test it, and I'm not going to worry about testing because I don't want you to really test anything. Is there any questions? The reason I don't want you to test anything is because there's no need. Because everything I'm going to give you is going to work if you do it correctly. Now you can ping and telnet. Now David's over here laughing because he knows he's going to be trying to test everything because nothing works for him. But still, it's the fact of the matter of what you need to do to learn the material. All right?